Okay, Assalamualaikum. Hi again. Okay, this is the second part for this slide, which is we'll cover on the switch mode regulator of DC to DC converter. Okay. Previously we did learn on the linear regulator, which is it only consists of a DC source, a switch and a load, which is in that example is R load. Yeah. Okay, so for switch mode regulator, we add more component in order to provide a better features for DC to DC converter. Okay, the function for switch mode regulator will be similar to linear regulator, which is it will convert the unregulated input into a regulated DC output voltage. Okay, and the regulation we can have the one that I mentioned previously, is either using a pulse generator or PWM control. Okay, so for switch mode regulator, there are two main mode of operation. The first one, what we call as continuous current conduction mode, or the short form is CCM. Okay, in this continuous current conduction mode or CCM, which means that the current must always be continuous, so the current cannot go to zero or negative. Okay, for this continuous current conduction mode or DCM, in this DCM mode, the current will go to 0 and negative. Okay, which means that at certain period of time there will be no current flow within the circuit. Okay, these are the basic switch mode regulator that will be covered in this lecture. So we go for focus on the buck, boost and also buck boost converter. Okay, so first we go to the buck converter. Okay, for the I think it's more or less the same as linear regulator just now. Okay, maybe in this next slide you will add the features of a switch mode regulator. Okay, a recap. Okay, for the buck converter, normally it will produce an output which is lower than the input. Okay, your output will be lower than your input, which is your input is higher. Okay, normally where does this DC converter, a buck converter, being applied? In DC power supply and also in DC motor speed control. Okay, so the integration over here is with regards to finding the average output voltage, which is you need to find this one here. Okay, remember, average you need to find the area under the curve over one switching time, obviously. Okay, but here we know that the output is 0, so you already know 0. So you just find what is identify the shape of the waveform and then find the area for that. Okay, this is a square, so the formula to find area for square is height multiplied by width. That is why you'll be able to get your average output voltage will be equals to D multiplied by Vs. Okay, the T will be cancelled out by our integration over here, 1 over T there. Okay, right. Okay, right. Okay, for switch mode regulator, okay, it works fine if you have a R load. The previous circuit just now, it worked fine if you have R load. But if let's say that your load is inductive load, so you have the inductor RL load, okay, so for inductive load, it's normally have this what we call as stray inductance. Okay, So this straight inductance, since we don't have any other alternative path or any other component, the only component that we have is our switch. Refer to the previous slide. Yeah, we have only our switch. So your switch need to absorb the inductive energy that being associated with the RL load. Okay, so this inductive energy will lead to damaging the switch because it will hit the maximum limit for the switch to handle the voltage. Yeah. So that is one problem with regards to stray inductance when the load is RL load. Okay, the second problem is that over here, okay, your output voltage will fluctuate from 0 to Vs. Okay, so you can see that just now in the waveform. Later I will show the waveform. Okay, how the voltage will be fluctuate from 0 to the value of your input voltage. So for example, if let's say that your input voltage, the value is 100 volt, so which means that it will fluctuate from 0 volt to 100 volt. So you can see it has a huge range of fluctuation. So this is very what we call is quite troublesome for the operation on the DC to DC converter. So normally it will not be acceptable because of that wide range of fluctuation. So how to solve these two problem over here? Okay, with regards to the first problem, when you have the R load, okay, we insert the what we call as freewheeling diode, okay, inside the circuit in order to provide alternative path for your current to flow when you have RL load or even R load. Okay, so it will provide alternative for your current to flow. For the second problem with regards to the fluctuation at your output voltage, we will have a low pass filter which consists of L and C filter, okay, in order to minimize this voltage fluctuation. Alright. Okay, so from the original circuit that only consists of a supply, a switch and load, now we have diode here, a freewheeling diode, and also a low pass filter here. Okay, this is the construction of buck converter. So you need to remember the construction for buck boost and buck boost, they are different. Okay, so for the buck converter, you have the input voltage. Remember, the diode here will always be connected in parallel with your DC input voltage. Okay, and then you have your switch over here. Selection of switch, you can have BJT, MOSFET, IGBT, GTO, it doesn't matter. Okay, and then you have the low pass filter over here in order to reduce the fluctuation that will be occurred at your output over here. Okay, alright. Okay, so when your switch is on, so since you have a switch and your diode, so when your switch is on, your diode need to be the other way around, which is your diode need to be reverse bias. So your diode need to be off in a way. Okay, right, and then so that the current flow will be from your input to your load over here. Alright. Okay, and when your switch is off, so if let's say that open circuit at your switch, okay, this is when your diode will become forward bias, and during this time, since you have the inductor over here, you know that the function of inductor, it will store the energy, right? So when your switch is on, it will store all the energy inside this inductor. So when your switch is off, this is when the energy from in the inductor will be released to the load in order to provide a continuous current flow in the circuit. Okay. Okay, with regards to the output waveform, it will be similar like the one that we seen previously. Okay, the turn on time will be equals to dt. Your turn off time will be equals to 1 minus t times t. Okay, then you get one switching time over here. Okay. Alright. Okay, this is the Vs amplitude, which is your the peak output voltage. Okay, the dotted line here, okay, is your average output voltage. Yeah. Okay. Alright. Okay, the waveform here in this slide, okay, we have the VL, which is your voltage across inductor. Voltage okay, voltage across inductor, and then this, the second waveform is your inductor current. Okay. Right, in order to produce these two waveform, okay, we need to have what we call as we need to do some analysis of the circuit. Okay, the analysis of the circuit will be based on the switch operation. Okay, so for when your switch is on, you will have one equivalent circuit, which is this one here. When your switch is off, you will have another equivalent circuit here. Okay, so from these two circuits, circuit number 1 and circuit number 2, then we'll be able to produce this waveform, these two waveform over here. Okay, so we will need to have the analysis of these two equivalent circuit in order to produce the output